Hello, thank you for joining me. This is the boat floating discussion that I didn't get to fit into the lecture on Thursday. So the way this works is that you have a man floating in a rowboat right here, and he has to get to a town. I add a little fire here. Maybe let's pretend his house is on fire, and he gets a cell phone message. So he has to get to the fire as quickly as possible. Now, you could imagine that he could just row all the way there. I guess he has a house on the lake. But the problem is that he rows slower than he runs. So maybe you could make it its smallest amount possible. He could just row straight and then run. But that might not be very quick either. So the question is, how do we figure out how to minimize the time? So clearly, we have to minimize two things. The time it takes to go that he goes to row, if he has some blue, and the time he takes to run, that's in green. So they tell you that town is a mile away from the edge here, and he's a mile out. So isn't that convenient? So if we let x be equal to the distance between the perpendicular distance from where he is now to where he decides to land on shore, you can see that this is going to be 1 minus x is the amount that he has to run. So just using Pythagorean theorem, the distance that he has to row is square root of x squared plus 1, which is right here. And so the time is always equal to the distance divided by the rate, right? So in this case, this time is 1 plus x squared. That's this blue part here. That's the distance divided by the rate. Well, in A, it says that he can walk 5 miles per hour and row at 3 miles per hour. So I divided it by 3 because he's rowing at 3 miles per hour. And then you add to that the second time, which is this distance here, 1 minus x, divided by 5, the rate at which he's running, right? And it says he's walking at 5 miles per hour. That's freaking running, if you ask me. And then you add those two together. Forget this one for a second. I'm just going to put that over there, okay? Okay, so let's see how this function works. Again, what we're saying here is I'm putting x in, this is x right here, it's 0.47, because remember this whole thing is 1. So if he decided to go about halfway, or whatever, what we can just do is say number calculate time of x. Okay, so where'd that go? Here it is. So what this is saying is it would take about 0.47 sevenths of an hour to do it that way. If we went all the way around here, it would take 0.53 or almost an hour, so that you can sort of see that this would take the most amount of time. It's also the largest distance, right? I think I'm going to make this to be much more so we can see little differences. So you can see it's going down. The total time is going down, 0.47, 0.46, 0.469, 0.47. Aha! So we can get this feel that at some point very close here, it makes it's quickest to row most of the way and then run the rest, which I don't know, both rowing and running are pretty strenuous in my opinion. So what we want to do then is, here's the graph, right? This is the graph of this function. So on the y-axis is the total time it's taking in terms of hours. And on the x-axis here is the distance along the shore. Sort of, you can think of it, this is the percent or whatever. So at 1 would be he went the whole way. X is what, where he went from the shore, where he landed on the shore. So the next thing that we want to do is actually take the derivative of this function. So I'm going to, because we want to find the tangent, I'm going to just hide this one for a second. And now you can see this is the tangent of the line, and notice that as I move this, you can watch the tangent. And as we know from the quiz and 100 other times saying it, right? that what we want this tangent line here to have a, we'll make it thick and I'll make it, how about orange? Right? We want this to have a slope of 0. So you can see here, this is the slope of the this is actually the equation of the whole tangent line. But you can see here the slope is about 0. And the question is, at what value for x is this 0? It's to be 0.75. If I make it a little bit more than that, you can see the tangent is starting to go up a little bit, which means it's the function is slightly increasing, meaning it's taking a little bit more time. So if I went 80% of the way rowing, I would take more time. So we can see algebraically, and we can see from the simulation here, that it should be 0.75. That's when the tangent has a slope of 0. Isn't this cool? All right, so now I'm going to go to because I know you guys are saying, well, we don't have technology, so what are we supposed to write? I know, I've heard you. So, I'm going to come over here now, and I hope you can read this, kind of. The idea here is you want to take the distance that he's going to row, that's distance 1 over the rate, which is the square root of 1 plus x squared over 3. The distance he's going to run, which is that second distance divided by the second rate. Since he runs at 5 miles per hour, you're going to say 1 minus x over 5. Then you're going, in order, the function that you want to minimize is the total time, which is time A plus time B. So time A here is 1/3 times the square root of 1 plus x squared. So I just wrote it with fraction exponent, so because I know I'm going to be having to take the derivative, right? And then this is 1/5 minus 1/5 x, or x over 5. So now I take dt dx, the derivative of time with respect to x, because you've got x's as the independent variable. So we have 1/6, a half times a third. This is the power rule. 1/6 times 1 plus x squared to the negative 1/2 times 2x. Don't forget the 2x, remember? That's the chain rule, because there's a function inside here. So see, all these things are coming back. And then this is going to be 0. The derivative of a constant is 0. And this is 1/5 times x. So that would just be minus 1/5. And we're going to set that equation equal to 0, or that expression. So I just multiply both sides by 6, and I get 2x over square root of 1 plus x squared is equal to 6 over 5. And then square the top, square both sides. So if you square this, you get 4x squared. And that obviously cancels out the square root. So you have 4x squared over 1 plus x squared is equal to 6 squared is 36 over 25. Then did a little bit of cross multiplication. 25 times 4 is 100x squared, and that's equal to 36 times 1 plus x squared, which is 36 plus 36x squared. And then I subtract 36x squared from 100x squared, I get 64x squared is equal to 36, and divide both sides by 64, and then take the square root of both sides, and you get square root of 36 over 64, which is 6 over 8, or ta-da, 0.75, which we had kind of already figured out. Now, that's the answer. But let's go back here and look at part B. Suppose that he can walk 5 miles per hour, but row 4 miles per hour. So what I have, now part B asks us an interesting question. It's saying, suppose now that we increase how fast he can row. So is that going to make a difference? So again, we do the exact same thing, except here, instead of dividing by 3, I'm just dividing by a, where a is 4, or I could make it any amount I wanted to. But this is one of the cool things about Sketchpad, is you can kind of play around with this. So what you see now is when we graph this second function, you can see that it's almost as if it takes the most time, again, if he goes this way, right, when x is 0. But as we go down, we see basically that this continues to decrease. So the total amount of time almost decreases completely. So let's show the tangent in this case. This equation here, right now it's saying it's got a slope of negative 0.3, but even as I move x all the way to the end, you still have negative 0.02. So what does that mean? That means that the function is decreasing because the slope is negative the entire time. So it never changed from decreasing back up to increasing again, which means if he runs at 4 miles per hour, the slowest is if he rows 4 miles per hour, the slowest would be to row the whole way. So that's kind of cool. One thing that you can do with this is you can actually change. Now you can see if it's at 3, they lie on top of each other because that's what the original function was. But as I increase it, the time, excuse me, the rate at which he rows, you can see that the total time decreases, and you still basically have a function that is also decreasing. So, which makes sense, right? Because he's rowing faster, so the amount of time is going to be less. So I really hope that this has helped. Now go and answer the online question that has the same context in it.